imagine that you launch a rocket vertically, and at one point there's a crosswind. So the effective wind velocity that the rocket sees is at an angle alpha from the rocket axis. Alright, this is, we'll call the wind velocity that the rocket sees v infinity. So after all, it's like we'll treat it in the following way. We'll treat it as if the rocket is still, and the velocity of the wind, well, better said, the incident velocity of the air is this would be due to the velocity of the rocket plus the velocity of wind, and plus we'll see some other terms which are not so obvious, but basically this incident air is due to the movement of the rocket plus the one of the wind. So when the rocket is at an angle of attack alpha, if it's correctly designed, the rocket will tend to stabilize. So what appears here is, let's see, yeah. Well, let's take a look at the forces that are present. So first of all, we have thrust, we have weight, which acts on the center of gravity. This is the center of gravity. We have weight. And recall we have one aerodynamic force. Okay, we'll call this, I don't know, F, which, if we project it on the axis of the rocket and the perpendicular to the axis of the rocket, we can decompose it to the normal force and the actual drag. Okay, let me change this one moment. Well, let's delete thrust because it's going to be a mess. But of course, if it's in the powered phase, thrust is going to be there. So we're going to have axial drag, A, and a normal force. And these vectorially add up to the aerodynamic force, which we won't see it much in that way. We always decompose it into axial drag and normal force. So axial drag is always there, but normal force only appears when the rocket is at an angle of attack. Okay, and this is the one in charge of stabilizing the rocket, because this normal force N is at a distance, let's call it epsilon for now, from the center of gravity. And you should imagine the center of gravity as if the rocket was pinned at this point, so it can oscillate around the center of gravity. So what the normal force is doing is it's creating a moment, a restoring moment, m, which is just the force times the torque, torque length. I don't know how to call this. All right, so the only moment we have here right now is the one due to the normal force. So the goal here is to understand how this normal force restores the rocket. So that's really all there is to stability. But as you'll see, it's there's a lot of juice to get out of. You can get out of here. So it seems like a simple problem, but it isn't. And so the first thing we got to do is predict the normal force. in function of flight conditions. So this could be angle of attack, the Mach number, and in function of the rocket, let's say the geometry. So we want to predict n, and also the position of the aerodynamic center, because this is the aerodynamic center is the position in which n actuates. All right, so the position of the aerodynamic center is x AC. If we take x as a coordinate from the tip of the nose tip, from the nose tip. So this is x equals 0, and the aerodynamic center is at distance x AC, and the center of gravity is at a distance from the nose tip x CG. So we have to know, the only thing that really bothers us is for stability, is the restoring moment. But we normally study it separately. We study the position of the aerodynamic center, and we try to model that, and we try to model the normal force. So if we want to predict N and AC for a rocket, and we will want to predict it in function of the flight conditions. So this could be the Mach number, this could be dynamic pressure, the angle of attack, basically these. And we also want to predict these two in function of the rocket's geometry. So maybe the diameter of the rocket, the length of the rocket, the length of the nose cone, and there's a lot of variables that define the fins. So let's just put fins. Maybe there's, I don't know, 5-10 variables that can define simple, some simple fins. Sorry, let me get this off. Yep, let's start to right click. Yeah, that's good. All right. So what we do to predict these two is to split the rocket and study the effects of our rocket parts, and then add their effects, add them up, to give, let's say, the overall, to get the overall rocket. What I mean by this is, we say that the rocket is basically a nose cone and a body. So rocket is nose cone plus body. Then we have the fins, and we'll study them independently. And then finally we have boat tail, which is this over here, which is like a conical transition that goes from this diameter to this diameter. So we're going to see why we add this, but basically I can tell you now that it slightly destabilizes the rocket, but it reduces the pressure drag a lot. So boat tail, I think it's written like this. We can add also here other conical transitions, but they're not so common. So what I mean by this is, imagine the rocket did, I don't know, like this. Oops. It went from this diameter to this diameter. Or, I don't know, it had a payload, so it went something like this, Like, imagine it had like this big fairing. But then it's not so common in some rockets, so just leave it to boat tail. So this is our rocket, and we'll study these parts independently, and I mean predict their aerodynamics and add the effects together. So what I mean by this is the fins will have a certain aerodynamic center and sorry, and a certain and a certain normal force. Okay, and AC. Well, we'll put that. Actually, we're going to move this back a bit because it kind of. Never mind. Just bear in mind that this is the position of the aerodynamic center of the fins, not the total rocket. So I'm not going to call it XACF. So I'm just going to call it. Where's the rubber? I'm just going to call it XF when I talk about the aerodynamic center of the fins, and I'm going to do the same with the rest. You can see now. So this is XF, which is the position of the aerodynamic center from the nose tip to here of the fins, and then we have the we gotta always add the center of gravity. Center of gravity is at the same place, of course, and yeah, the center of gravity, we don't take the center of gravity of the fins or the bow tail or the body. We just use the general rocket. So this is the same. So then we have the body and the nose cone. They have their never mind. Their aerodynamic center in the nose cone, and which is at a position from the nose tip. Let's call it XB. And it has another normal force when it's flown at an angle of attack alpha. And finally we have the bow tail or other conical transitions. I think I'm messing up. Yeah. It has its own aerodynamic center. We call it XC for conical, and a normal force. All right. So what this means is that the overall effects of the added parts. Okay, so if we add the effects of the fins plus the bow tail plus the body and nose cone, it's going to be exactly the same as having one normal force at another aerodynamic center, an aerodynamic center of the whole rocket. And so, give me a sec. Alright, let me get back to where I was. What I mean is that if these two systems are equivalent, this is like saying that the normal force in this system, so the total normal force, is equal to the sum of the forces here. So this is the total normal force is equal to the normal force due to the fins plus the normal force due to the body and the nose cone, and due to the conical transitions. So, and that's not the end, because oops, damn, oh what, what's happening? Give me a sec. Alright, sorry for that. I'm still getting used to this. Oh no, not again. Sorry. I don't know, for some reason it's getting buggy, but okay, let's try to get back where I was. So if the two systems are equivalent, the total force has to be the same and the total moment has to be the same. So the moment here, I'm not going to try moving again because I'm going to mess up. But the moment was the total normal force times the distance from where the force is applied to the center of gravity. So moment is m equals n times e epsilon, which we can now call the distance from the aerodynamic center to the center of gravity. This is equal to all the moments on this system. So it's going to be the moment due to the body, and here, well, the distance from the aerodynamic center of the body and nose cone to the center of gravity. So we'll call this xb minus xcg, and the same with the fins and the conical transitions. And you can see here that the direction of these forces, these normal forces, they're not arbitrary. So, and let's draw alpha again here. At this angle of attack, at a positive angle of attack, we're going to have the normal force due to the fins are going to try to restore the rocket. And although the nose cone and the body have the normal force on the same direction, because the aerodynamic center of the body and nose cone is above the aerodynamic center, you actually have a moment that's fighting to actually increase the angle of attack. So it's going to be and the boat tail is fighting, let's say, against the fin, so it also destabilizes. So the boat tail and the nose cone plus body destabilize, and the fins are going to stabilize. If this were to be a positive conical transition, this would be stabilizing, but that's rarely seen. So after all, you're having like a fight between the fins and the body and nose cone. The boat tail, this force is pretty small. The lengths of the normal forces are arbitrary, but the directions aren't. So this force is pretty small, and we're actually gonna say it's near to zero in the future videos. We're going to see about stability. You're going to see why it simplifies the equations a bit. So if we don't have any fins at all, well, we're only going to have a non-corrective moment, which is due to the body destabilizing it. So we have fins, and we have them on the back. The most we can on the rear side, because, well, if we put some fins here, well, the aerodynamic center of fins practically, let's say, well, 25% from its tip. Okay, so this would be the aerodynamic center of these pairs of fins. So that's why, and these fins would destabilize. Okay, so why do you see fins like above, not on the rear side of a rocket sometimes? Well, just model rockets to sometimes copy missiles, and in missiles you do have active control. And when we're talking about active control, it's completely another thing. You usually have these fins which are above the center of gravity that are destabilizing, but they move, which are called canods. But yeah, we're not going to cover that. We're not doing missiles, we're doing passively stabilized sounding rockets. So this, yeah, we're not going to cover these, but it makes, for model rockets, it just destabilizes it, but because it's a copy of missiles that do have active stabilization, well, they just keep them, but they, yeah. All right, so from this equation, you can actually get the position of the aerodynamic center of the whole rocket. Okay, if we take this at the other side, and this is just this, well, you can find the position of the aerodynamic center.